Hi everyone, this is Jyoti Bolanawar, Assistant Professor in Computer Science Department, Government First Grade College, Narega. Today we'll deal with the second part of mathematical logic, which includes these contains, that is logic implication, laws of logic, laws for the negation for the conditional, second one transitive and substitution rules, third one duality, next logical implication, valid arguments, rules for inference. These are the topics today we are going to deal with in the mathematical logic part 2. First, we'll see what is laws for the negation of conditional. As we know, conditional is nothing but implication. If P is true, if P is true, then Q is not true. That is, for a given conditional P implies Q, its negation is obtained by using the following law. That is, negation of P implies Q is logically equivalent to P and negation of Q. The proof for this, how we can prove that, prove this law is by using the truth table. Here we can see the truth table. We have a two proposition like P and Q, and these are the possible truth values for the P and Q. As we know, P implies Q is false only when P is true and Q is false. In remaining cases, the P implies Q is true. So negation of P implies Q. Here the first possibility is if P implies Q is true, negation of P implies Q is false. Similarly, for the remaining option, remaining possibility, and this is the negation for the P implies Q. The illogical equivalence for this is, first we have to identify negation of P. The negation of P is nothing but what? If not P, Q. If Q is false, negation of Q is true. If Q is true, negation of Q is false. If Q is false, negation of Q is true. Similarly, negation if Q is true, negation of Q is false. Okay, then ANDing of P and negation of Q will be P and 0. If P is 0, negation of P is 1, P and Q. Only the AND operation, if both the prepositions are true, then the result will be true. In other cases, it is false. So P is false, negation of Q is true. So the result will be 0. Similarly, in 0 and 0 is 0, 1 and 1 is equal to 1, and 1 and 0 is 0. Here we can see in this column and in this column we can see for all the possible combination we have a same truth values. Therefore, the negation of P implies Q is logically equivalent to P and negation of Q. This is called law for the negation of condition. Okay, and here are the some table of laws for the summarization of negation of the compound preposition. If the preposition is negation of Q, then the negation of P is P. If preposition is P and Q, then the negation of that is negation of P or negation of Q. If the preposition is P or Q, then negation of that is negation of P and negation of Q. If the preposition is P implies Q, then the negation for that is P and negation of Q. Here let's consider here an example. Let X be specified number, any number. Write down the negation for the condition. Okay. Consider the statement. If X is an integer, then X is rational number. This is P implies Q. So we can split this compound preposition into simple preposition like P. We can consider X is an integer. Q preposition we can consider as X is a rational number. According to the negation rule for the conditional, we know that negation of P implies Q is logically equivalent to P and negation of Q. So we can write this implication in negation form as X is an integer and X negation of Q is X is not a rational number. Okay, this is what negation for the given implication, that is if X is an integer then X is a rational number. Next rules are transitive and substitution rule. The transitive rule states that if we have a prepositions like U, V and W such that U is logically equivalent to V and V is logically equivalent to W, then we can say that U is logically equivalent to W. This is known as transitive rule. Okay, then substitution rule. Substitution rule states that suppose we have a compound preposition called U, which is tautology. That means for all the possible truth value, the result will be true only. And the P is a component of U. If you replace each occurrence of P in U by any other preposition Q, then the resulting compound preposition V is also a tautology. That means if you replace in a given compound preposition, if you replace any compound preposition by in some other preposition, then the truth value will be again tautology only. That we can say, that is called a substitution rule. Next is duality. Duality means if you have a compound preposition U that contains the connectivities like conjunction and disjunction. Suppose if we replace the occurrence of conjunction with disjunction in U by disjunction and conjunction respectively, then the resulting compound preposition is called dual of U and it is denoted by U raised to D. Let's consider here example. The given compound preposition is U conjunction, Q disjunction negation of R, disjunction yes conjunction true. Okay, how we can write the dual of this is, symbol for duality is U raised to D. If U is a preposition, the dual of this is U raised to D. This is a representation. And here we can say just what we have to replace here. We need to replace conjunction by disjunction and disjunction by conjunction. That means wherever we encounter with the and, then that has to be replaced with the or. Wherever we encounter with the or, there we have to replace with the and if there is a true value, then that has to be replaced with false. Okay, that is if P as it is, here we have a conjunction that has to be replaced by disjunction. Then Q, again here we have disjunction that has to be replaced by conjunction. The negation of R we have to keep as it is. Then the negation of here we have what conjunction, disjunction, then that has to be replaced by conjunction. Then S, again conjunction replaced by disjunction. The truth value is replaced by false value. Then the following are the two results for two important results, that is duality of a compound preposition. If you make again dual, then it will be a original preposition. Dual of dual is original preposition. Second important result for this duality is for any two preposition U and V, if U is logically equivalent to V, then duality of U is again logically equivalent to duality of V. I hope it is clear. Same example here we can consider. Wherever we encounter with a disjunction, replace with conjunction. Wherever we encounter with conjunction, just replace with the disjunction. These are the simple two examples. You can go through them. Next is logical implication. In this logical implication, we have three terms like converse, inverse, and contrapositive. Consider then how to write a converse, inverse, and contrapositive for a logically implied preposition, that is compound preposition, that is P implies Q. Then how we can write the converse, inverse, and contrapositive for this logical implication. That is converse, if we have a preposition P implies Q, the converse of this preposition is Q implies P. The inverse will be negation of P implies negation of Q. Contrapositive will be negation of Q implies negation of P. Okay, here we can see the truth table for inverse, converse and contrapositive. We can go through the truth table for all the possible values. Then we have the two results for this logical implication, that are a conditional and its contrapositive. Conditional and its contrapositive are logically equivalent. We can see here, this is a conditional for P and Q, that is P implies Q. We can observe the truth value here for all the combinations. Then it is logically equivalent to contrapositive of this conditional, and this column is a contrapositive. We can observe here the column that is P implies Q is, all the truth values are same or similar to negation of Q implies negation of P. That indicates what? P implies Q is logically equivalent to negation of Q implies negation of P. One more important result here is converse and inverse are logically equivalent. Converse means what? If we have a conditional P implies Q, converse of this is Q implies P. Here we can observe the logical truth values here for Q implies P, and next the inverse of this is negation of Q implies negation, negation of P implies negation of Q. We can observe all the truth values are same, so we can say these two are logically equivalent. Okay. Next, how we can prove this logical implication? We have hypothetical or implicative statement. What do you mean by hypothetical or implicative statement? If we have a conditional P implies Q, where P and Q are related to in some other way, so the truth value of Q is depends on truth value of P and vice versa. Such a conditionals are called hypothetical or implicative statement. Andre, if we have a condition like P and P implies Q, P and Q are some way they are related. In how they are related, the truth value of Q depends upon the truth value of P, or the truth value of P is depends on truth value of Q. In such type of conditionals are called hypothetical or implicative statements. Okay. When if we have a hypothetical statement, that means dependent statements like P implies Q, such that Q is true whenever P is true, because the truth value of Q is depends on the truth value of P. Say that P implies Q, and we can symbolically write it as P implies Q, and this symbol denotes the word implies. Okay. When the hypothetical statement such that Q is not necessarily true whenever P is true, that is, we say that the P does not implies Q. How we can write it symbolically? It does not implies. This is symbol for does not implies. Okay. Then we have necessary and sufficient conditions here. Consider two prepositions P and Q whose truth values are interrelated. Like what? If P is true, then Q is true. If that means truth value of P is depends on Q and vice versa. If P implies Q, then in order that Q may be true. Okay. That is, it is sufficient that P is true. Okay. Q, whether it is true or false, but the sufficient that for any condition or any logical implication, P should be true. That is sufficient that we can say the Q is true. And also if P is true, then it is necessary that Q is true. The following statements are like carry the same meaning. If P implies Q, then P is sufficient for Q and Q is necessary for P. Here we can say we can see the example: state converse, inverse and contrapositive for the given condition. The given condition here is if triangle A is not isosceles, then it is not a equilateral. How we can write the converse for this is, converse is, this is P implies Q anta tagondre, then if triangle if the triangle is not equilateral, then it is not isosceles. Inverse of this is if the triangle is isosceles, then it is equilateral. Contrapositive for this is if triangle is equilateral, then it is isosceles triangle. Okay, these are some examples. We can go through in the reference books for more examples. This is also write down the following in the necessary and sufficient condition language. Here we have a preposition like an integer is odd if and only if it is divisible by, and only if it is not divisible by odd. That is necessary and sufficient condition that integer is odd, that it is not divisible by 2. Okay, next we have arguments in a prepositional logic. Then what is this argument? Argument is a prepositional argument in a prepositional logic is a sequence of prepositions. Till now we have seen simple prepositions and compound preposition. Now if we have a sequence of prepositions, then that is called argument. Let's consider set of prepositions like P1, P2, P3 up to Pn, then the preposition Q. Then a compound preposition in the form P1 and P2 and P3 and Pn implies Q. This is called argument. That means these are sequence of prepositions. Okay, and this sequence of preposition, if you write in this given format, then that will become a argument. And here this P1, P2, P3 up to Pn are called premises of the argument, and Q is called the conclusion of the argument. How we can represent the argument symbolically means P1, P2, P3, P4, so on up to Pn. Okay, these are the sequence of prepositions which gives the next new preposition called Q. And here we see the 3 dots. The 3 dots stands for therefore. Next, if we have an argument, then we need to check the validity of the argument. That means when we can say that argument is a valid argument. Okay, if the argument is said to be valid if whenever each premises like P1, P2, P3 up to Pn is true, then the conclusion Q is true. In this case, whenever we have a sequence of premises, all the premises are true, then the conclusion will be true. Then we can say that the given argument is valid argument. How we can write them symbolically as follows: P and Q, P1 and P2 and P3 and P so on up to Pn implies Q. That means these all are true, then which implies this is true. And it is to be emphasized that it is argument, the premises are always taken to be true, whereas conclusion may be true or may not be true. If the conclusion is true, then we can say that the given argument is valid argument. Okay, this is again representation of valid argument form. By the definition, when we have if the argument is valid, we have a premises like P1, P2 up to Pk, then conclusion is Q. Then we can say when the given argument is valid means P1 and P2 and P3 so on up to Pk implies Q is tautology. That means premises should be true and conclusion should be true. Then we say that the given argument is valid argument. Important definitions we can say: basically argument is nothing but sequence of prepositions or statements. We can say them as a premises, and that ends with what? Conclusion. Then validity means the deductive argument is said to be valid if and only if they take the form, it takes a form that makes it impossible for premises to be true and conclusion nevertheless to be false. If the premise is true idaga, definitely the conclusion should be true. And such arguments are called valid argument, and we say that that is a validity of the argument. Falsity to the incorrect reasoning or mistakes which leads to a invalid argument, such as they are called false. Structure of the argument, how the structure should be an argument. As we know, they are the sequence of statements called the premises P1, P2, P3 up to Pn. The conclusion is represented with Q. If P1 and P2 and P3 so on up to Pn implies Q is tautology, then argument is termed as a valid, otherwise it is a invalid, or we can write as first premises, second premises up to end premises, therefore the conclusion. This is the form for this is the form to represent the valid argument. Here are some examples. If it rains, I drive to school. This is one premises. It rains is a second premises. Therefore, I drive to school is a conclusion here. We can write them in the form of sequence of premises like P. Let's consider P. It rains. Q. I drive to school. Then argument belong to the following form. It can take in this form, as we can see here. If it rains, then I drive to school. Then we can represent it as P implies Q. Then it rains. It rains means it is a preposition or premises P. Therefore, I drive to school. I drive to school is nothing but Q. That is, P implies Q, P. These two are the premises. Therefore, the conclusion Q. This is similar example. This we can represent it as P implies Q, and this if I study discrete mathematics, then I will get A is Q implies R. Here we have written what is P. P it knows Q. I will study discrete math. R I will get A. The premises are here. If it snows, I will study discrete maths. If I study discrete math, I will get A. Therefore, the conclusion, if it snow, then I'll get A. We can represent symbolically like this. These are a few more examples we can follow. Next is rules for inferences. Rules for inferences, they are used to check the validity of the argument by using these simple rules. Such as first one is addition, and these rules are called rules of inference. First one is the addition rule. According to addition rule, if P is a premises, then we can use the addition rule to drive P or Q. That is, P is a premises, therefore conclusion is P or Q. This is simple, and it is called addition rule. Here consider example. Let P be the preposition. He studies very hard is true. Q is the preposition. He is very bad student. Okay. Therefore, either he studies very hard or he is very bad student. Second one is conjunction. Conjunction is defined as follows. If P and Q are the two premises, then a conclusion for the conjunction rule is P and Q. Okay. P implies as P is a first premises, Q is a second premises, therefore conclusion is P and Q according to the conjunction rule. Here P, we can consider he is very hard, he studies very hard. Q is he is best boy in the class. What is the conclusion here? He studies very hard and he is best student, best boy in the class. Next is third rule is simplification rule. According to simplification rule, the premises P and Q is true, then the conclusion conclusion is P, which is also true. Example we can consider: he is very hard, he studies very hard, and he is the best boy in the class. How we can write this is premises P and Q. He studies very hard and he is the best boy in the class. Therefore, he studies very hard. Next, fourth rule, modus ponens rule. In this, two premises are P and P implies Q are the two premises. If these two are true, then the conclusion Q is true. According to this, consider example: you have a password, you can log on to Facebook. These are the two prepositions. Then what are the premises here? P implies Q. That is, if we have a password, then we can log on to the Facebook is the first premises. Then second premises is if we have P, that is if we have that is P, that is you have a password. Therefore, the conclusion you can log on to the Facebook. This rule is called modus ponens rule, and this is used for checking the validity of the argument. So fifth rule is modus tollens rule. According to this is if P implies Q and negation of Q are two premises, then the modus tollens used to derive negation of P. This is the what rule of modus tollens, that is P implies Q, negation of Q, therefore negation of P. Here again we have a same example here, that is you have a password, you can log on to the Facebook. That if P implies Q, we can write like this: if we have a password, then you can log on to Facebook. Negation of Q we can write like we cannot log on to Facebook. Therefore, negation of P, we do not have a password. Sixth one, disjunctive syllogism. According to this, if negation of P and P or Q are two premises, then we can use disjunctive syllogism to derive Q. Okay, this is symbol for disjunctive syllogism, and this is an example. If P is the ice cream is vanilla flavored, Q is ice cream is chocolate flavored. Negation of P we can represent as the ice cream is not a vanilla flavored. P or Q can be represented as the ice cream is either vanilla flavored or chocolate flavored. Therefore, conclusion is ice cream is chocolate flavored. Next one, hypothetical syllogism. According to this, if P implies Q and Q implies R two premises, then we can derive P implies R by using the hypothetical syllogism rule. So example for this is if it rains, that is if P consider as it rains, Q is I will not, I go to school or I will not go to school, that is P implies Q. If I don't go to school, then I won't need to do homework, that is Q implies R. Therefore, P implies R. If it rains, I won't need to do homework. Next, resolution. According to this rule, if P or Q and negation of P or R are two premises, then we can have a resolution rule to derive the conclusion Q or R. Here example, same example, we consider if P is I will study discrete math, Q is I will visit Las Vegas, R as I will study database. How we can represent P or Q here? I will study discrete math or I will visit Las Vegas. How we can represent negation of P or R as I will not study discrete math or I will study database. Therefore, conclusion we can write as I will visit Las Vegas or I will study database. Next is universal instantiation in universal UI. This according to this rule, how we can represent this is for all x P of X, therefore P of C for any C. That means if for any given domain, if you consider domain as a all students and Sachin is a student, okay, yeah, according to this all students are smart, therefore this Sachin is smart. Next, universal generalization. Universal generalization, according to this, if P of C for any arbitrary value you can for C, therefore for all X, P of X. That means if you any particular the given rule is true for all, if a given rule is true for a single person or a single value, then it will be true for all the values which comes under a particular domain. Similarly, existential EI, that is there exists a X P of X, then P of C for some element of C. That is, there is someone who got A in a computer science. Let's call her let's call her one name with and say that she got A. Next, existential generalization, that is P of C for some element C, then there exists X P of X. That means she got an A in class, therefore someone got A in the class. Okay, these are the 12 rules for the inferences. Okay, I hope it is clear. And these are the some of the reference book we can refer for more examples and more definitions. Thank you.